Okay, we saw last time the definition of a ring. This is some basic properties of rings. So here's a pretty easy theorem. Let's suppose I have a ring. Then I could say a few things. The first thing I could say is 0 times A is equal to A times 0, which should equal 0. So 0 is the additive identity in the ring. Negative A times B is the same as A times negative B, and that's negative AB. When I put a negative in front of an element in the ring, that means the additive inverse to the element. So negative AB is the additive inverse to A times B. And third, negative A times negative B is AB. So two negatives give you a positive. So here's the proof. The first statement follows pretty quickly. I have 0 times A is the same as 0 plus 0 times A. 0 is the additive identity. So 0 plus 0 is 0. Using the distributive law that's in the definition of ring, this is 0 times A plus 0 times A. Now, additive inverses exist. I could subtract. Subtraction is illegal in a ring. So in a ring, intuitively, you can add, subtract, and multiply, but maybe not divide. So I could subtract 0A on both sides and get 0 is 0 times A. So that's the condition where 0 is on the left. It's a very similar argument to when 0 is on the right, so I'm going to omit that. So I'm going to claim that's the statement number 1. So that's statement number 1. Statement number 2. Statement number 2, I got to prove that starting with 0. That's A minus A times B. So A minus A is 0, and based on property 1, 0 times B is 0. Now I can use the distributive law. This is AB plus negative AB. Subtraction is legal in a ring. So I'm going to subtract AB on both sides and get negative AB is equal to negative AB. So that proves this part of statement 2 when the negative sign is on the A. And it's a very similar argument for when the negative sign is on the B. So I'm going to omit that as well. I'm going to claim that I'm done with property 2. And then why is the product of two negatives a positive? Why do two negatives cancel out when you multiply them? Well, negative A, negative B, using property 2, I have a negative on the A, so I could factor out the negative. So this is negative A times negative B. So I used property 2 with the negative on the A, factoring it out. Now I can use property 2, factoring out the negative on the B. So this is, negative AB. Now the inverse to the inverse is itself. So this is just AB. So that's the proof of properties that you probably expected should happen in a ring, and they do. Okay, let's make a few definitions. These two definitions that I'm going to make to end this video should be familiar from our study of group theory. So let's see. A subring of a ring R is a subset of R that is also a ring. This should be reminiscent of our definition of subgroup, but it's a subset of R that's also a ring. In particular, you have to have the two binary operations plus and times be closed on your subring. So to check for if we have a subring, you need to check. So you need to check if both ST and S minus T are in the subset for all S and T in the subset. So you have a subset of a ring. You want to think, is it a subring? Well, these are the two things you have to check. Is it closed under multiplication? If I take two things in my subset, multiply them, do I get back in my subset? Is it closed under addition, and does it have inverses? Well, those two conditions are checked simultaneously for addition by checking that S minus T is in your subset. So to check if you have a subring, you need to check these two properties. So for example, upper triangular matrices are a subring of all n by n matrices with coefficients in C, for example. It's a subring because when you multiply two upper triangular matrices, you get back an upper triangular matrix. And the difference or sum of upper triangular matrices is again upper triangular. So that's one example of a subring of n by n matrices. If I change that to, say, invertible matrices would not be a subring because invertible matrices are not closed under addition. Okay, so our next definition is that of a ring homomorphism. So let R1 and R2 be rings. So a ring homomorphism that's what I'm defining, is a function phi that goes from R1 to R2 such that two things hold. Number one, phi of A plus B can be split over addition. So this is phi of A plus phi of B. Now this plus sign here, A plus B, that is the addition in R1. This plus over here, since phi takes R1 to R2, this would be the addition in R2. And phi also interacts nicely with multiplication. So phi of AB is phi of A, phi of B, and both conditions 1 and 2 are true for all A and B in your ring R1. It's ambiguous here possibly, but I think we're getting sophisticated enough to realize that this AB is the multiplication in R1, whereas this multiplication, phi A, phi B, that's the multiplication in R2. So this should be very familiar from our study in group theory. It's almost the definition of a group homomorphism, except I have two binary operations. Phi has to interact nicely with both of them. So let's do a couple of examples. I can define a function that takes z to zn. I could define it by phi of a is a mod n. That is an excellent example of a ring homomorphism. We've seen in previous course that you can break up modular arithmetic over sums and multiplication. So we've seen before that this is an example of a ring homomorphism. Why don't I do one more example? Why don't I go from polynomials in X with coefficients in R and send that to R. R itself is a ring because I can add, subtract, and multiply. So I'm going to define a function which takes polynomials and gives you numbers. And I'm going to define it by sending a polynomial px to p of 7. So I'm going to plug in 7 into my polynomial and get a real number out. I'm evaluating my polynomial at 7. This is also a homomorphism. This is a homomorphism. You could check it. I don't know if I really want to right now, but this is definitely a homomorphism. It's actually a pretty useful one. This is the evaluation homomorphism. Evaluation homomorphism is the homomorphism you get by plugging in a certain value into X for your polynomial, getting back an element in R. All right, great.